Hello everyone, this is the first of many lectures that I will be sending out to you throughout this course. And let's do a quick recap of what we learned in the previous class. We learned the concept of resolution, which is the minimum distance between two objects that you can see clearly. And we also realized that that is dependent on the wavelength of the light itself. So optical microscopes which rely on the visible wavelength ranges are unable to resolve below 300 nanometers, and that is laid out by the Rayleigh criterion. We learned about the wave-particle duality and its concept that was proposed by de Broglie, and how he said that if you increase the energy of an electron, the wavelength diminishes. So if you tie that to the Rayleigh criterion, the higher the energy of an electron, the smaller is the wavelength. The smaller the wavelength, you have a tighter airy disk. That means you have a higher resolution. That's the entire principle on which electron microscopy stands. We learned about the concept of brightness and how it is constant throughout the electron column in an electron microscope. We learned about the equation and how it is related to the temperature, which states that the brightness is inversely proportional to the operating temperature of the electron source. Therefore, you don't want to operate the electron source at a very high temperature, but if you end up doing it, it is at the cost of the brightness. Okay. All right. So here is a basic comparison. I had shown this chart previously in the class, and as I said, higher operating temperatures result in a lower brightness. So if you compare the tungsten filament to the LaB6, you can immediately see as the operating temperature goes down, the brightness goes up. And then there are another class of electron sources called the Schottky field emission sources, or the cold field emission sources. We'll talk about that in the next lecture, but you can see they operate at much lower temperatures, which essentially translates to a higher brightness. And you want more brightness for good imaging. Okay. All right. So the size of the electron source is critical, because essentially what you want to do is decrease the probe beam, that is the beam that is finally incident on your specimen or your sample. So you want to decrease the probe beam diameter down to about 10 nanometers or lower. But if you start with a beam electron source, if the beam diameter is in the order of tens of microns, that means you have to scale it down over a factor of 2 or 3, which becomes a problem. But then there are ways to go about it. So basically, the smaller the size of the point of emission, the smaller is the source size. That is ideal. And so the goal is to shrink the diameter of the probe current to typically a few nanometer. That enhances the spatial resolution that you see in your images. Right? Again, along with the operating temperature, it is important to note that the stability of the electron beam is also uniform over time. So you don't want to be taking an image. Sometimes acquiring an image can take up to a few minutes, and you don't want the emission current or the electron source fluctuating while you're taking an image, because that's going to end up deteriorating the quality of the image that you see. Okay, so when we accelerate at about 20 kilovolts, that's just for example, the energy that the electrons get is about 20 kilo electron volts. And so you want the energy spread of the electrons to be as minimal as possible. That means you want a higher fraction of the electrons coming at exactly and precisely 20 kilo electron volts. If there is a difference in the energy of the electrons, or there's a spread, essentially that translates to a larger airy disk, because higher energy or a spread in the energy is basically a spread in the wavelength, and a spread in the wavelength means you have different diameters in which you can confine the airy disk. So now you have a blurry airy disk if you have a larger spread in energy. You don't want that. So A larger spread in energy is also associated with electrons going in different velocities. That basically means you have different focal points or different diameters of the AD disk, and you end up getting a blurry image. So the mode of electron generation determines the energy spread. If you look at the table here, because the energy spread in thermionic emissions in case of tungsten or LaB6 is higher compared to the Schottky field emission or the cold field emission processes, they are typically inferior in nature, right? So we have been seeing this in the table so far, but just to lay it out, you have thermionic emission, which is used in majority of the electron microscopes around the world, but then you also have these really expensive field emission microscopes of electron sources, which are significantly more expensive. And basically you have different processes and physical principles involved in the way they emit the electrons, and we're going to get into those. So let's start with thermionic emission. So the process of thermionic emission was first coined by Owen Richardson from England, who received the Nobel Prize in 1928 for the work he did. He basically said that electrons, if they have to stay by themselves in vacuum or in air, they require tremendous amount of energies. So you cannot simply knock off an electron from the surface of a metal unless you give it a ridiculous amount of energy. And the amount of energy you give is the work function of the material. So if you were to take a piece of gold versus a piece of iron versus a piece of palladium or platinum, each and every metal has its own characteristic work function, which means you have these signature amount of energy that you need to give to electrons from the respective metals for the electron to escape the surface of the metal, right? So the work function is energy. So you measure it in electron volts, and it is related, and the amount of electrons that go out of the surface of the metal, which is basically the current density, is related by the equation that is given here, right? So let's take a while and understand this equation. So you have the current density J, which is equal to a constant which is called the Richardson constant. I don't want to get into the details of what makes up this constant, but let's say that is characteristic of a material, right, of any given metal or any given semiconductor. It is proportional to the square of the temperature. So higher the temperature, you have a higher current density, right? And then there's also an exponential term here, which is the negative of the work function over Boltzmann constant times temperature, which means you need to increase the temperature of the surface of the metal so that this term becomes more than 1. Only then you will start seeing some value in the current density. Okay. So here is a band diagram. You have the valence electrons, you have the Fermi level, and the Fermi level is by definition the energy at which all the electrons are located, right? And then you have the conduction band in a metal. So you apply a significant amount of energy, which is the difference between the vacuum level and the top part of the conduction band, right? Then that is the work function. So you apply that energy by in terms of heat, so that's thermal energy, right? So you apply that, and then the electron escapes and it travels across, and that is what we see as an electron in the electron beam source, right? So from the previous equation, we know that the work function, the exponential term had the work function over the Boltzmann constant times temperature. So lower the work function, the easier it is to knock off the electron from the surface of the material, right? That means at a lower temperature, you'll be able to achieve the same thing for a material which has a lower work function, which is why the LaB6 is better in terms of the electron density that you can achieve from that source compared to tungsten. So in case of tungsten, which has a work function of 4.5, you need to go to higher temperatures to initiate the process of thermionic emission. Okay, and I want you to go over all the details of the different values that are here, just for comparison. You don't need to memorize any of it. It is just for you to appreciate the differences between the two sources. Yeah, tungsten is a good choice for the thermionic process because it has a melting point of 3660 Kelvin. I don't know how much that is in Fahrenheit. You can translate that. I can't. I mean, you can do the conversion, but I don't know it off the top of my head. But LaB6 is definitely a much better source simply because it has a lower work function. Okay, so let's take a look at the assembly of the electron gun for a thermionic emission. Usually these are triode gun assemblies, which means there is an emitter. So the emitter is the source right here in pink. Then you have a ground plate, which is the Wehnelt cylinder. Yeah, and then you have a you have a ground plate, which is the anode, and you have the Wehnelt cylinder, which is the electrostatic lens. Okay, so you apply a negative voltage to the source, and that emits the electrons out of the tip of the tungsten filament, right? So here is an image of the tungsten filament, and here is an image of the Wehnelt cylinder, and let's get into the details of it. I'll talk about the circuit and everything in the next slide. So if you take an SEM image of the filament itself, it is really small. So you can see the diameter of the tungsten wire is about 100 microns. So you heat this single filament to a very high temperature of about 2500 degrees Celsius, and that is when the thermionic process begins. There are several advantages to tungsten. I spoke about it in the previous slide, that it has a high melting point. It has a low vapor pressure, which means once you start heating it, it does not degas. And degas is a process in which you have stuff coming off of the surface of any material. It could be some kind of contamination. It could be just adsorbed oxygen molecules, or any kind of contamination that is coming out of a material as you heat it. That process is called degassing. So the vapor pressure of tungsten is low. It does not degas. It's not porous, right? So if you have pores within the material, it can degas more than a material which has minimal number of pores. So it's solid, and it is a high tensile strength, so it does not really break as you thin it down into the shape of this filament. Of course, everything has a lifetime, and from time to time, if you suddenly ramp up the temperature or you do something, everything breaks down in time. So you can end up getting filaments that look like this, that are broken, then they need to be replaced. Sometimes you can improve the ductility, which is the process in which you beat it down to a wire by doping the tungsten with rhenium, right? So let's talk about the triode assembly. You have the filament. There are two circuits involved here. One is circuit which is associated with heating of the filament itself, right? So you apply a voltage across the filament. It's really high voltage, so that the temperature goes up to about the operating temperature of 2500 degrees Celsius. And then you have another circuit, which is a circuit which accelerates the electron from the tip of the emitter as it is generated. Okay, so the Wehnelt cylinder is basically a metallic disc, a metallic cylinder with a hole on the top, right? So now you have these electrons that come out from the emitter, but these electrons are all over the place, which means they are going at different angles everywhere. What this Wehnelt cylinder does is it is biased at a slightly more negative voltage than the tip itself. That is done by the bias resistor over here. So now if you have electrons, those are negatively charged, and if they see a plate around them which is also negative, they are repelled by it, right? So the only way the electrons see that they can go out is through the hole here, and these are the electrostatic field lines that actually guide the electrons out of the Wehnelt cylinder. If you did not have the Wehnelt cylinder, what would end up happening is the electrons would go everywhere. They would just spray out of the tip of the tungsten, and then you could not get any directionality. So it's very important that you have the Wehnelt cylinder, which gives directionality and focuses the electron to a point. And this point is very significant. That is called the crossover point. Essentially, you can think of it as an image of the tip of the filament right here. Yes, the crossover point is also, or the diameter of the crossover point is also called the beam diameter, as it is emitted out of the electron source. Now, the anode, which is the positive terminal, is the one that is generating the energy for accelerating the electrons right through the electron column, right? So this is where you apply those tens or hundreds of kilovolts between the tip of the filament and the anode. The Wehnelt cylinder is simply a focusing mechanism, and so the electrons, once they go past the crossover point, they again take a conical shape, and they are accelerated down the anode. At this point, there are several electromagnetic lenses that are below the anode, and we'll talk about that later. But this is the general assembly of the tungsten filament triode assembly. Yes. Okay. Now, the Wehnelt cylinder is critical in focusing and making sure that you collect as many electrons as possible at the crossover point. But it is also important that you realize that the biasing of the Wehnelt cylinder is critical, simply because, let's take a look at this figure here. You have the anode. So the anode and the tip of the filament generates the potential for accelerating the electrons right through it. Now, if you have a Wehnelt cylinder that is unbiased, right, which means now the electrons are sprayed in a conical fashion, or that's a solid angle, right? Think of it in 3D, and then you lose a lot of them because the brightness is low, simply because not all of them are focused into so that they pass through the anode. At the optimum bias, you focus them at a point and then they pass through the anode, and so that's great. That's what we are shooting for. But now if you increase the negative potential on the Wehnelt cylinder, that means now you have these electrons that are coming off of the tip, but instead of going past the hole in the Wehnelt cylinder, they're just getting scattered all around because there's too much repulsion from the negative potential on the Wehnelt cylinder. So the electrons just can't go by, and then you have a sharp decrease in the brightness of the electron column itself, and that is captured in this figure over here. So on the x-axis, you have the potential that you apply to the Wehnelt cylinder. The y-axis is the emission of the current that is coming off of the tip of the filament, right? And then you have the brightness also on this axis on the right, which you want to maximize as much as possible for a given electron source. So the position, this position here, which is associated with 1, is the case of an unbiased Wehnelt cylinder. So you have some electrons that make through it. The emission current is high, but the brightness is on the lower side, right? So this blue curve is your brightness curve, and the gray curve here is the curve of the emission current. Now, if you look at the case number 2, which is the optimum bias case, you have all the electrons focused. So now you have majority of the electrons passing through the anode, so the brightness goes up. Now, if you keep increasing the bias on the Wehnelt cylinder, so now the electrons that are coming off of the emitter are repelled back, or they get scattered, so they are unable to go past the anode. Obviously, there are no electrons going through it, and the brightness tremendously drops, and that is not where you want to be. Now, this is all in the case of a certain accelerating voltage that you give to the anode. So let's say this is the diagram or the calibration curve when the anode was at 20 kilovolts. Now, let's say you're doing an imaging and you crank up the voltage on the anode to 30 kilovolts. So this calibration curve does not hold anymore. So now you need to have a different bias to the Wehnelt cylinder so that it is still focusing and going past the anode at a different accelerating voltage, right? So this whole thing is controlled by the electronics itself. The optimal bias is controlled by the electronics of the self-regulating bias resistor. And that's really good, because you don't want to calibrate at different voltages to achieve optimum brightness. Yes. And now let's go back to the circuit 1, which is the circuit essentially responsible for heating the filament. So as you increase the temperature of the filament by increasing the current in the circuit, yes, you don't see any emission at all. And then suddenly you see some growth. We'll talk about the false peak in a bit, but you suddenly see some growth, and then it increases exponentially until it flattens. And that is associated with that exponential term in the current density equation that we saw a couple of slides earlier, right? So when you hit when you're close to the temperature which is equivalent to the energy of associated with the work function, that is when you start seeing some electrons coming up, and then they suddenly rapidly increase, and then at some point they flatten. And you want to operate in this regime, because it is at this point when the curve is flattened is when you have a stability in the emission current, right? So if you have any fluctuations in the potential, your filament is not going to be affected, because it is operating at a temperature where it cannot increase the brightness any further, or the current density will not increase. So tungsten filaments are really cheap. They can be replaced. We do that all the time over here. They last about 100 to 150 hours of operation time, that is beam on time. They have a slightly higher energy spread, but for most of the operation that we do, it is acceptable. Of course, you cannot achieve very high resolution simply because of the higher energy spread, or let's put it this way, you cannot achieve the resolution you would with a cold emission gun. And of course, it's a low brightness image. So the beginning of the electron beam manufacturing, most of the sources were tungsten filament, until later there was more development in how to improve, and the cold emission guns were developed. So apart from the tungsten filament, we also have the LaB6, which is something, it has a similar operation procedure, but it has slightly different. There are slight differences, and let's talk about that. So LaB6 is a material which has a lower work function, which immediately tells you you don't need to heat it up to 2500 degrees Celsius that you would do for tungsten, but you can operate at about 1400 Kelvin. They have low vapor pressure similar to tungsten. They have good chemical and thermal stability. But LaB6 is an insulator, so you cannot pass current through LaB6 the way you did for tungsten. Yes, so what you have here is a sheet of copper which is placed right below the LaB6 emitter or the crystal, and you heat the copper up, which in turn, by virtue of conduction, heats up the LaB6. Okay, and these tips are really sharp. The crossover diameter that you get for a LaB6 is about 5 microns compared to 50 microns for tungsten. Just to remind you, the crossover diameter is the diameter of the electron beam once it passes the Wehnelt cylinder, after it is focused through the Wehnelt cylinder. Okay. All right. So this is just a basic schematic. You have some stainless steel rods holding it all up, and this is the vitreous carbon is what you use to heat the LaB6, right? So you apply a voltage between the two plates here, which heats up the carbon, and that in turn heats up the LaB6, and then you get emission. Okay, so again, a summary. Just pay attention to the details. to the operating temperatures, the brightness, the energy spread. So you can see here both thermionic processes have higher energy spreads of about 2.5 electron volts compared to field emission guns, which we will talk about in the next lecture. But then they offer reasonably good stability over time, so which is why they're used. Plus, they are cheaper compared to the field emission guns. Okay, so we'll talk about the field emission guns tomorrow. And as I always refer to them, they are the Lamborghini of e-guns. They're really expensive, but they're really sweet with amazing performance. Okay, that's the end of it. Bye-bye.